This video lecture is meant to cover the information found in Unit 15 on acids and bases, covering objectives numbers 5, 6, and 7, where we will be identifying acid and base pHs on the 0 to 14 pH scale. We'll be describing how the concentration of hydrogen ions and hydroxide ions are related in an aqueous solution. And we will quantitatively analyze the pH of a solution from the concentration of hydrogen ions and the concentration of hydroxide ions, as well as the other way around, and determine if the solution is acid, base, or neutral. To start out our discussion on pH, we have to understand that there's something called an ionization constant for water. And even though water is a molecule, molecules typically do not separate into ions, but water is a special molecule that does dissociate into ions, although weakly. As in not strong, not once a week, but it will partially ionize according to this equation seen here. And so liquid water can spontaneously break apart into hydrogen ions, that's an H+, and hydroxide ions. We're ignoring this, that should not be included in this sentence. We're going to skip that. But it turns out by experiment, the hydrogen ion concentration, meaning the molarity of the hydrogen ion concentration, multiplied by the concentration of the hydroxide in solution, is always equal to 1 times 10 to the negative 14. And so that's what we call the ionization constant for water, or sometimes it's abbreviated as Ka, the K for constant, A for acid. So the product of the concentrations of hydrogen ions times the hydroxide ion concentrations will always be equal to 1 times 10 to the negative 14. So if you have a solution of pure water, which will be neutral, then that means the hydrogen ion concentration should be equal to the hydroxide ion concentration. You can think of it this way, because the hydrogen ion concentration represents acids and hydroxide represents bases. If you have an equal amount of acids and bases, it's going to be neutral. And what happens is, in order for mathematically, if they're equal and their product has to multiply out to 1 times 10 to the negative 14, then each one of those concentrations has to be 1 times 10 to the negative 7. Because 1 times 10 to the negative 7 times 1 times 10 to the negative 7 equals 1 times 10 to the negative 14. Okay, but in an acidic solution, there has to be more hydrogen ions than hydroxide ions, and in a base solution, just the opposite. There has to be more hydroxides than hydrogens. But no matter which one of those three scenarios, where they're equal to each other, or where the hydrogen's concentration exceeds the hydroxide concentration, or just vice versa, the hydroxide ions exceeds the concentration of hydrogen ions, the product of those two concentrations must always equal 1 times 10 to the negative 14. So what that really means is that in any acidic solution, there will always be some hydroxide ions, and in any basic solution, there will always be some hydrogen ions. Bottom line, this is equilibrium, and so there will always be some products and some reactants. Okay, so you're always going to have all three of those things in solution. It's just a balance of, if there's more hydrogen ions, it's an acid. If there's more hydroxide ions, it's a base. That's really what it comes down to. Okay, let's see how this translates to pH, which stands for the power of hydrogen, otherwise known as the hydrogen ion concentration. Okay, now remember, in our previous discussion, hydrogen ions or protons don't exist just found solo in water. They are found piggybacking on a water molecule to become the hydronium ion. So if I use the hydrogen ion symbol or the hydronium ion symbol, we're really talking about the same thing. Well, pH is the negative exponent of the hydronium or the hydrogen ion concentration, which is the same thing as saying pH is the negative log, and I'm going to rewrite this because I realize I just wrote over it. It's the negative log of the hydrogen ion concentration, same thing as the hydronium ion concentration. But we're going to keep these problems really simple, and so long as our concentrations are expressed with a coefficient of 1, then we're not going to need a calculator to use the log function, right? And so it'll turn out that whatever our exponent is here, taking the negative of that exponent, the negative of the exponent will equal our pH. That's what a log function does. Now, if you had some number other than 1, you would have to use the log function because that just complicates the math a little bit. So here's the thing. Remember what we said is that the hydrogen ion concentration here and the hydroxide ion concentration, those two numbers when multiplied have to be equal to 1 times 10 to the negative 14. So let's take a look at pH of 1. Notice that our hydrogen ion concentration is 1 times 10 to the negative 1. Okay, remember, when you have the concentration expressed as 1 times 10 to a power, you take the negative of that exponent and that becomes your pH. Okay. Well, if you know the pH, you then can figure out the hydrogen ion concentration, and consequently, you can find the hydroxide ion concentration. 1 times 10 to the negative 1 times 1 times 10 to the negative 13 equals 1 times 10 to the negative 14. Notice that those two exponents just add up to 14, or negative 14. So with a pH of 4, that means the hydrogen ion concentration has to be 1 times 10 to the negative 4. And the hydroxide ion concentration, therefore, is 1 times 10 to the negative 10. Multiplying those two numbers, you get 1 times 10 to the negative 14. And of course, that will continue all the way down. A pH of 7 is 1 times 10 to the negative 7 for the hydronium concentration, and 1 times 10 to the negative 7 for the hydroxide concentration. A pH of 10 has a hydrogen ion concentration of 1 times 10 to the negative 10, which means that our hydroxide is going to be 1 times 10 to the negative 4. A pH of 14, now we're getting a very minuscule amount of hydrogen ions, 1 times 10 to the negative 14. But we'll have a lot of hydroxides by comparison, 1 times 10 to the 0, which is really just 1. Okay, and we're talking about, but these are all concentrations, and I suppose I should have mentioned the concentrations are all expressed in as molarity, moles of solute, divided by liters of solution. Okay. And note, the hydrogen ion is the same as the hydronium ion as per our initial discussion on acids. All right, let's take a look at the next page, which is a closer study of pH. pH is a measure of hydronium ion concentration. And notice that I've been using brackets. The brackets, you read that as, you know, it's the concentration of hydronium ions, or hydrogen ions, same thing. And really, it's expressed as molarity. Okay, so if you have the hydrogen ion concentration is 1 molar. That's as a regular expanded number. How would you express that number in scientific exponential notation? Well, that would be 1 times 10 to the 0. From that, you can easily see that the pH is 0. And we can also figure out the concentration of hydroxide, right, which we can get from this number right here, because those two numbers, the exponents have to add up to negative 14. So the concentration of the hydroxide is going to be 1 times 10 to the negative 14. So a pH of 0 has a lot of hydrogens and very little hydroxides. Okay, if we have a concentration of hydrogen ions to be 1/10 molar, 0.1 molar, that's 1 times 10 to the negative 1, which means the pH is 1. And our hydroxide ion concentration is 1 times 10 to the negative 13. If we have a concentration of 0.01 molar hydrogen ion concentration, in exponential form, that's 1 times 10 to the negative 2. So our pH is 2. And our hydroxide ion concentration is 1 times 10 to the negative 12. An acid concentration of 0.001 molar is expressed in exponential form as 1 times 10 to the negative 3. So that's a pH of 3, and the hydroxide ion concentration is 1 times 10 to the negative 11. Okay, this keeps going on as we make the acid less and less concentrated. We're now at 1 times 10 to the negative 4 hydrogen ions, making it a pH of 4, and a hydroxide ion concentration of 1 times 10 to the negative 10. So you can see here, as the acid progressively gets more dilute, the pH increases towards neutral, and if we were to continue going on and on, we would see that this would then flip over past the neutral point of 7 and into the basic pHs. Okay, let's take these numbers that we just saw in this chart and we're going to plot them so you can see what a logarithmic function looks like on a graph. All right, and the numbers are up off the screen. But if you take a notice at what we're going to do is we're going to plot pH versus the hydrogen ion molarity. And if we see that the original molarity was 1 molar, so that's here, and we saw that the pH was 0, well, that's that point right there on that line. At 0.1 molar, that's here, way over here on the left side, we saw the pH was 1. Now this is going to get harder. 1/10 of a tenth, so now we're looking at, 1/100th, that's here, that's a pH of 2. And then 1/10 of that, well, that's going to be even closer to here, and then eventually it's really just approaching the 0 mark. And so a logarithmic function has this really stretched out part of the curve for much of it, but then the rest of it is crammed into a very small space. And this is why if you've ever used log paper, that's what log paper helps to even out all those intervals. All right. So what this is trying to demonstrate is that there is a logarithmic function relationship between pH and the hydrogen ion concentration. And that's pH is equal to the negative log of hydrogen ions, which is the same thing as pH is the negative log of hydronium ion concentration. All right, we're going to put this into a little bit more practicality. And again, we're not going to have to use the log function for our work because for this class, we're going to stick with all the coefficients are all going to be 1, which, as I said before, eliminates our need to use the log function on a calculator. So let's step back for a moment. We have a pH scale that starts at 0 and goes to 14. Halfway through that is 7, which is neutral. Anything from 7 to 14 is a base, and it gets progressively more basic as you approach 14. Anything less than 7 is an acid, and as you go from 7 towards 0, it gets progressively more acidic. All right, so let's take a look here. The first chart shows hydrogen ions being 1 times 10 to the negative 5th molar. Okay. From that, we can tell that the pH is going to be 5 because we took the negative of the exponent. And we can also figure out that the hydroxide ion is going to be 1 times 10 to the negative 9 because those two exponents have to add up to negative 14. A pH of 5 tells us that this substance is acidic. If our hydrogen ion concentration is 1 times 10 to the negative 11, the hydroxide is 1 times 10 to the negative 3. Our pH is going to be 11, which makes this a base. A hydrogen ion concentration of 1 times 10 to the negative 7 will have a hydroxide ion concentration of 1 times 10 to the negative 7. The pH will be 7, and this will be neutral. If we have a hydroxide of 1 times 10 to the negative 3, our hydrogen ion concentration will be 1 times 10 to the negative 11. The pH will be 11, making this a base. 1 times 10 to the 0 hydroxide ion concentration will give us a 1 times 10 to the negative 14 hydrogen ion concentration, making this a pH of 14 and therefore making this substance a base. I'm going to leave the last one blank for you to try on your own. Number 2, here I'm giving you the pH. From that, we have to find the hydrogen ion concentration and say whether it's acid, base, or neutral. Well, just from the pH alone, a pH of 2 is an acid, a pH of 4 is an acid, a pH of 9 is a base. Okay. If the pH is 2, then the hydrogen ion concentration is 1 times 10 to the negative 2. A pH of 4 is a hydrogen ion concentration of 1 times 10 to the negative 4, and a pH of 9 is 1 times 10 to the negative 9. If you are given hydroxide ion concentration and asked to find the pH, what you first have to do is think about, well, what does it take to find the hydrogen ion concentration? Because you know those two numbers have to add up to negative 14. So you know that the hydrogen ion concentration has to be 10 to the negative 12, making the pH 12. If the hydroxide is 10 to the negative 11, then the hydrogen ion concentration has to be 10 to the negative 3, making the pH 3. If the, this is supposed to be 10 to the negative 7, the print didn't work all that well. If the hydroxide ion concentration is 10 to the negative 7, then the hydrogen ion concentration is also 10 to the negative 7, making the pH 7. And then from there, you know, the pH greater than 7 is going to be a base, pH of 3 is going to be an acid, and then the pH of 7, of course, is neutral. Finding hydroxide ion concentration from pH. Okay, well, first of all, pH of 13 is going to be a base. pH of 4 is going to be an acid. pH of 8 is going to be a base. If we know the pH is 13, then that means the hydroxide ion concentration is going to have to be 1 times 10 to the negative 1. If the pH is 4, the hydroxide ion concentration is going to have to be 1 times 10 to the negative 10. If the pH is 8, the hydroxide ion concentration is going to have to be 1 times 10 to the negative 6. Okay, so there you have it. That is how far we are going to go with the pH from hydrogen ion concentration and hydroxide ion concentration. That's it for our discussion on pH. We'll see you in the classroom.